Hi guys, okay, once again welcome back to the think class of operating system concepts. Okay, right now we are going to discuss something about high level linguistic synchronization constructs. And before going and beginning this topic, let's go to our traditional some humor concepts or thought-provoking concepts. So the so for today, the thought-provoking concept is like, if the exposure of body is modernization, then animals are more modern than humans, right? So just think about this concept. Now, now let's begin the session. Okay, so what are the critical regions then? So critical regions are something that are categorized as a high level linguistic synchronization constructs, okay, and they are very high, okay, in performance. That's why this is the thing, right? So if you go and check out, you will also see something like variable, something a shared variable, okay, while inside a critical region we have some shared variables, and these shared variables are declared in some certain statement that is shared tv, and t stands for the type and v is the variable, and this is a shared variable, and this is shared among all the other processes, okay, inside a critical region. And these shared variables can be accessed by another statement, that this is called region, okay, and this is a shared variable to something, that is a statement, okay. So while statement s is being executed, so statement will be executed, so statement s will be executed here. And also the next idea is like, while the statement s is being executed, no other process can access the shared variable. So accessing these shared variables and executing this kind of statement, all the other statements will not be able to access this kind of shared variable. Okay, and these variables can be used by a single process at a time. That means only one process can access this shared variable, right? So this was the concept. And also there are some other more concepts that you have to understand, is that this statement like shared, that is declaring a shared variable and accessing the shared variable, this statement are very useful, and this will repeatedly occur in our programming language and further lectures. Okay, so be careful about this shared statement and this region statement to access the shared variable. Now, so what are the nested critical regions then? Nested critical regions are something that are accessing the critical region, and inside the critical region there is another shared variable which is accessing the another critical region. So like, let's see, we have declared here two shared variables, that is v of type v, shared variable v of type v, whereas shared variable w of type w. And inside the region v, shared variable v, we do something, we call this statement, and we begin, we just perform some action, and we access another shared variable, that is w, region w, do something. So this is the situation. It is like nested, okay, something like this. Region w is accessed like shared variable w is accessed within shared variable v, right? Now, what are the inner construct of this shared keyword and the region keyword then? Okay, if you go and check out, we already noted that shared variable is just to declare the shared variable, right? Shared keyword. And how is actually it is doing inside? What is inside? Here is like the type define the structure of this like tag, and this type of this particular type, the value is type of this value is declared, and the semaphore mutual exclusion semaphore is also called from here, and then directly we create another variable of this type, that is of this structure, consisting of this kind of parameters, right? Parameter that is a value of type t and a semaphore. Now inside the region, while this region statement, which is mostly used to access the shared variable, is what it is done is we initialize the mutual exclusion, that is initialized to 1. That means it is free, the semaphore is very free, and we wait for the semaphore, and then we execute the statement and then signal out the semaphore, right? So this is the inner concept of the of these keywords, shared and region keyword, right? Okay, now what are the problems with these nested critical regions then? The nested critical regions that we implemented before. So what can be the problems that will particularly occur in this kind of nested critical regions? And this kind of problems, the problems that might occur is like 2 or more processes wait indefinitely for the event to occur, that is mainly caused due to one block event. Okay, for example, if you go and check out here, this is P. In the process P, we like what we state is like the region, we try to access region V, the set variable V, while we try to access set variable W, and then the statement 1 is executed. Okay, so whereas also in Q, we try to access set variable W, whereas we also try to access set variable V and then execute the statement S2. So if you check out very carefully, like in process P is signaling out set variable mutual exclusion of set variable V, whereas process Q is waiting for mutual exclusion of set variable W and is waiting for that. So unless it gets the signal of this set variable W, the mutual exclusion of set variable W, it is not going to print out the statement, it's not going to execute the statement. So there is some kind of deadlock situation. Okay, so this process is signaling out mutual exclusion of set variable V, whereas this is waiting for mutual exclusion of set variable W, and this is signaling out mutual exclusion of semaphore of set variable W, whereas this is waiting for semaphore of set variable V. So there is some kind of situation, okay, which is indefinitely, which is mainly occurred due to one block event and affecting so many other events, right? So how to solve this problem of producer and consumers with the critical regions then? If you go and check out, I have described here it in a program right here, and what we have done is we similarly I told you that we always use the shared variable, right? First we declare the shared variables that are the message buffer of maximum value, the max, whereas also the integer for these are the integer for the indexes for producer and consumer respectively, which are initialized to 0, whereas also the semaphore variable, the semaphore are full and empty. Okay, semaphore variable are just initialized to full is initialized, semaphore is initialized to 0, whereas empty is initialized to max. And now inside the producer, what we do is we try to access the shared variable, okay, by using the statement region, and B is accessing to P, semaphore producer, and then we perform this statement, okay. And after performing after accessing the shared variable, we perform this, we execute this statement, and then we signal out the semaphore, that is a full, and inside the consumer block consumer is waiting for the full signal from the producer, and after receiving this full semaphore, it accesses the critical region by using the statement region, and then execute the statement and signal out the empty semaphore. And similarly the producer will receive this empty semaphore and starts its activities, and similarly this goes on indefinitely. Okay, and this is how to solve the problem with the critical region. And also, now what is the next question then? So what are the critical regions which are very conditional, that is conditional critical regions, CCR? These are the conditional critical regions, are the critical regions, okay, which is mostly used by this statement, that is region accessing the critical region, like shared variable b when the statement b is true and do the following statement. So this is the statement is something like this. So when a process tries to execute the region statement, the Boolean expression of b is evaluated. So this is evaluated when this is true. So if this is true, the statement b is evaluated. Okay, so and the statement s is executed, whereas else the process is delayed. Okay, and that means it waits until this b statements becomes true and no other process is in the region associated with this shared variable b. Okay, so these are conditional critical regions here. Okay, now how to solve this producer and consumer problem using the conditional critical regions then? Okay, while you try to solve the problem using the conditional critical region, as I have already stated here, we have to check the certain condition here. And also all the similar constructs are similar to like the solution of this previous one, that is a producer and consumer problem solution with critical region. All the construction are similar, but the only difference is like we use the conditional check. So the conditional check is applied here, like if the counter is less than the maximum value, the max value of the buffer, then similarly it accesses the critical region and performs its job. Okay, and signal out the semaphore, and it is received by the receiver. And okay, also in the receiver there is some conditional check, that is when the counter is greater than 0, then access the critical region and perform your statement, perform your job, right, in this receiver state. Sender state is also doing, and the receiver state also doing after they satisfy this kind of conditional check. And this is just a way to solve the producer and consumer problem using conditional critical check. Okay, now there is another statement that is like just like before, like we checked with while, there is also a wait condition. And what is it, this conditional check doing then? This is the conditional check in which it is used when a process can execute the process. This process can execute the statement 1 accessing the shared variable b in mutual exclusion before testing the Boolean expression, that is before testing this Boolean expression b, and can be posterior. So before testing, if we use when, it should test this condition, but if you use this like the keyword await, that means this statement will be executed before checking this Boolean expression. Okay, so this is the difference. And now like we will try to show you the implementation of the statement, that is reason b do when b do some statement. Okay, check the Boolean expression, then perform the following statement. Now for every variable, okay, like we declare share the compiler produce Okay, every variable v declared and shared, the compiler produce the structure with the following fields. That means v is the value, and mutex is something like a semaphore for mutual exclusion that protects the shared variable v. So delay is something semaphore that blocks the process when the condition v is false. Whereas count is something that number of processes blocked on the semaphore delay is counted. Whereas temp is the count of number of processes in the list of semaphore delay, okay, that has already tested the condition after the process has lived its critical region. Okay, something like this. So if you check out, the simple idea is like the condition check. If the Boolean expression is not true, then you perform such action. Otherwise, the statement, do something with this reader value. That means you access the shared variable and perform the statement, and also you do the check this conditional check. Okay, this is greater than 0, then you signal out the delay, else you signal out the mutex, right? So similar conceptual idea is also performed here. Now, okay, so describe the readers and writers problems then. Okay, so there are in a classes of process called readers that can access a database in parallel manner, right? Whereas there are also classes of process that are called writers. So class of process means there are a bunch of processes. Class of process that are called readers, and class of processes which are called writers that also must access a database in mutual exclusion with other writers and reader processes. Okay, so during the access of this writer to the database, several reader and writer processes can be blocked outside their critical region. So there are not only one writer process or reader process which are accessing the critical region. So many other classes of this particular process are waiting outside to access the critical region, right? So how to manage this kind of readers and writer processes who are waiting outside the critical region is termed as a readers and writers problem. And the only basic concept you have to understand is we have to avoid the deadlock, okay, in this situation. So this problem of avoiding the deadlock in this kind of waiting situation of readers and writers is termed as readers and writers problem. So we can solve this problem by either giving precedence to the readers or precedence to the writers. Okay, so I shall explain you some solution of giving precedence to the reader and solving this readers and writers problem, and similarly the precedence to the writers and solving the readers and writers problem. Now let's check the situation of giving precedence to the readers. So as you know, the several readers and writers processes are blocked outside the critical region. So in this situation, the precedence is given to the reader, that means favor the access of waiting readers, okay, rather than waiting writers. So if you check out the code, first what we have to do is we have to initialize the variable. These are the reservation for readers, okay, number of reservation that is done for the variable that defines the number of reservation that is done for the readers processes. This initialized to 0, whereas the semaphore are initialized to 1. That means semaphore are free. Okay, semaphore are free, that is not occupied. So whereas in the readers process, what we do is we wait for the mutual exclusion and we increment the counter of this following readers. So you can initialize, or you can reserve how many processes you want. You can also reserve to x numbers, so you can reserve from 1 to x numbers, okay. So while you increment the counter, so after waiting for mutual exclusion semaphore, you increment the counter. Then if the counter after implementing the variable is the number of reservation made is 1. That means that there were no waiting readers right outside. That means your initial the reservation was just 0. That means you wait for the semaphore W and you signal out the semaphore. Okay, so you wait for the semaphore W. That means if you have just only one reservation, just wait for semaphore W. Otherwise you signal out the mutual exclusion and you start reading, because you have so many other waiting processes of readers. So the precedence is given to all these reading processes, and lastly you wait for semaphore ME, then you decrement the counter. Then after decrement the counter, if this is just to check that if the process was just 1, that means even after implementing, like if the process was 1, then after decrementing it will go to 0, right, the counter. Then if it is just only one process that was waiting for the readers, then only you signal out, you just perform and just signal out the writer. Okay, and after signal out, the signal out is received by this writer and it performs its writing actions. Okay. And also you signal out the mutual expression, that was the semaphore just to check out. Okay, among so many other writer classes of writer processes. And similarly, this is performed here. The precedence is given more to the readers in this situation, right, rather than writers, because writer have to wait to this semaphore W, because this to signal out from this reader to semaphore W to start this writing process, right? Whereas similarly in the writer's precedence to the solution of the readers and writers problem, the waiting writers are given more preference than the waiting readers. So you can also see that the reservation is done here in this variable, and you initialize the mutual exclusion semaphores. Whereas in reader you can check out, like reader waits for all the semaphore, waits for reader, like R semaphore, mutual exclusion 2 semaphore, mutual exclusion semaphore. Then lastly it increments the counter of reservation. So if the reservation is similarly, if the reservation is 1, then there are no waiting readers, so you just wait for the semaphore W. Okay. Whereas then you signal out the mutual exclusion, you signal out mutual exclusion of R, then signal out also mutual exclusion 2, then you start reading process. Okay, then similarly you also check that if after decrementing the count, like the reservation counter is 0, then you signal out the W. And whatever, and the concept is like also here, like in the writer the precedence is given to the writer, so what it does is just wait for semaphore mutual exclusion semaphore 1, it increments the counter. Okay, checks if it is just 1, that means just 0 writers are waiting outside, that means just wait for the reader to signal out. Okay, then it signal out the mutual exclusion 1, semaphore waits for W semaphore. Okay, waits for this reader semaphore and start writing, signal out the W semaphore, and then similarly the checking situation is done here. So similarly the idea is like writing is given more preference here rather than reading, because reader has to wait for so many semaphores before performing these reading actions, right? Whereas and also signal out the particular semaphore, so that the writer it has to just wait for this one semaphore mutual exclusion 1, and you start checking the situation, then just perform its writing actions. Okay, this was all about this high level implementation of semaphore, right? the linguistic synchronization construct. Now we will continue more about the upcoming topic. Maybe the upcoming topic will be the last topic of our session for this operating system concepts, and after that also we will continue with more programming concepts that are mostly related with the laboratory, like implementation of the programming concepts of operating system. Okay, so thank you for listening.